Hi, I'm Ping-Lun from National Taiwan University, and our work is about an efficient and flexible BFT protocol simulator. Byzantine fault-tolerant protocols allow a distributed system to reach consensus by exchanging neural messages between participating nodes. Because these protocols can tolerate less than one-third of the nodes to be faulty or malicious, they are usually applied to critical systems such as aircraft systems or blockchain systems. Since BFT protocols are usually applied to critical systems, we need rigorous security proofs to make sure that they can function properly. A BFT protocol needs to satisfy two security guarantees. The first one is safety, which makes sure that all the honest nodes share a consistent state, and they will not generate conflict results when a consensus is reached. The second one is liveness, which ensures the consensus will eventually be reached after a certain period of time. However, FLP impossibility states that a BFT protocol cannot provide safety and liveness at the same time in an asynchronous network. Because most network environments in the reality are asynchronous, this caused a difficult situation for BFT protocol designers to design a protocol that satisfies safety and liveness at the same time. To overcome this impossibility, a lot of BFT protocols assume a partially synchronous network, which allows them to achieve both safety and liveness. Theoretically, a partially synchronous network assumes a global stabilization time, or GST, such that all packets can be delivered in a bounded transfer time after the GST. In reality, however, network delays are usually unbounded, and network attacks can make the network environment extremely unstable. In these cases, theoretically analyze a BFT protocol's performance is almost impossible. So, how can we evaluate the performance of a BFT protocol in a more realistic setting? Our work solves this problem by simulating BFT protocols under a real-world situation. The reason we choose to use simulation to study a BFT protocol is that it provides several advantages over theoretical analysis or actual implementation of a BFT protocol. The advantages are: first, we can evaluate the overall performance rather than only calculating the communication complexity, which theoretical analysis can only provide. Second, we can simulate various network environments, such as different distribution of network latencies and connectivity between nodes. Theoretical analysis can only assume a simple network model, and an actual implementation also requires some network simulation to achieve this. Third, we can simulate a BFT protocol under various attack scenarios, while these scenarios are usually too complex to analyze theoretically. Other than these points, simulation can also provide high efficiency to reduce experiment time, and it is much easier to deploy when compared to a real implementation, and even more. However, simulation also comes with some limitations. One example is that our simulation result can be different from the actual behavior of a real system, which can be caused by some implementation bugs of our simulator or the BFT protocol. To solve this issue, we added a validator module to our simulator that can compare the simulation result of our simulator with a ground truth, such as the execution trace generated by a real system or another simulator. Another limitation is that there are some aspects of a BFT protocol that cannot be easily captured by simulation, such as the calculation cost. We think this is not a big issue because the network latency usually is much larger than the computation time, especially when the system is deployed in a wide area network, as for the case of public blockchain systems. Now, I will talk about our BFT simulator. Before I introduce the design of our simulator, I want to point out how our work stands out from the existing BFT simulators. Even though previous work already proposed some BFT simulators, our work provides several significant improvements. First, our simulator has much better performance, which allows us to simulate more number of nodes. How we achieve this is by using a simplified network. Since the behavior of BFT protocols is only affected by the network latency, the detailed behavior of the network is usually not important, such as TCP, IP, and other network layers. Therefore, we only transmit the protocol messages, and we neglect all other network layers' messages. We also do not simulate the topology of the network and only control the connectivity between nodes. This allows us to further simplify the network while preserves the high flexibility to add specific rules between nodes. Another distinct advantage of our simulator is that we can simulate a wide range of attacks, while existing tools can only provide a limited set of attacker models. One example is that we can simulate various network attacks. Our design allows an attacker to access and control each network packet so that the attack scenario can be easily customized for each pair of nodes. Furthermore, an attacker can gather information from the honest nodes before deciding which nodes are faulty nodes, allowing us to support an adaptive attacker model, while existing tools usually need to specify which nodes are Byzantine nodes beforehand. Our simulator also provides a very convenient functionality that can visualize the execution trace of a BFT simulator. This allows researchers to understand BFT protocols at a glance, and BFT protocol designers can also utilize this functionality to make sure that their protocol behaves the same way as expected. The diagram on the right illustrates the structure of our simulator. There are four major components. The first one is the controller, which manages all events inside an event queue, and it will dispatch events to other components, and other components can also register events with the controller. The second one is the consensus module. This is where the BFT protocol lies in, and it controls the behavior of honest nodes. When nodes need to send messages to each other, they deliver their messages to the network module, which is the third component. The network module determines the latency of each message, passing the messages to the attacker, and finally deliver the messages to the controller as message events. The last component is the attacker module, which is a global attacker that can view or modify network messages. By modifying or inserting new messages, the attacker module can simulate the behavior of Byzantine nodes. By changing the network latencies or dropping some of the messages, the attacker can simulate a network attack. The user of our simulator needs to provide a configuration file which specifies which BFT protocol will be simulated and the number of nodes, the network environment, and the type of the attacker. After the simulation, our tool generates a result that tells the time and message usage of the protocol and the execution trace of each node for more detailed information. Let's take a closer look at the consensus module. We provide a flexible design such that we can support several different kinds of BFT protocols. In addition, it is fairly easy to extend our simulator to support other BFT protocols. To add support to a new protocol, apart from its protocol logic, only a handler for message and time events and a communication interface to the controller are needed to be implemented. We currently implemented the following BFT protocols: 3 versions of ADD plus BA, Algorand Agreement, Async BA, PBFT, Hsiao with a naive view synchronizer, and Libra BFT. To make sure that our implementation can correctly reflect the behavior of the BFT protocol, we also added a validator module to our simulator to compare our simulation results with execution traces generated by other tools, and we used this validator to check the correctness of our PBFT implementation. One unique characteristic of our structure is that we simulate Byzantine behavior using a global attacker, and this allows us to have a flexible design that can easily support various types of attacks. To implement a new attack, only the attack logic and a handler for message and time events are needed. As a demonstration, we currently implemented 5 attacker models. Fail-stop is a trivial attacker that does not send any messages. Network partition is an attacker that can block the communication between some pairs of nodes. Static attacker decides the set of floating nodes before execution, while the adaptive attacker can choose which nodes to be floating nodes during the execution. Finally, a rushing attacker can decide its action after observing the messages sent from honest nodes. Using our simulator, we discovered several interesting experiment results. The first experiment I want to discuss is comparing the performance of our simulator and BFT sim, which is an existing BFT simulator. This diagram illustrates the simulation time required by our simulator and BFT sim to simulate PBFT. The x-axis is the number of nodes we simulate, and we simulate from 4 nodes to 512 nodes. The y-axis is the simulation time used by these simulators in seconds. Note that both axes are using log scale. It can be seen that our simulator uses much less time than BFT sim. When simulating 32 nodes, our simulator is 500 times faster than BFT sim. In addition, our simulator can support 512 nodes or even more, while we encountered an out-of-memory error when using BFT sim to simulate more than 32 nodes. This experiment is about simulating BFT protocols under various network environments. These diagrams illustrate the time and message usage of different BFT protocols when they are simulated from a fast and stable network to a slow and unstable network. The x-axis of both the diagrams are indicating the type of BFT protocol, while the y-axis in the left diagram is the time needed by each BFT protocol to reach a consensus, and the y-axis in the right diagram is the number of messages transmitted by nodes when they are reaching a consensus. Initially, we simulate these protocols under a network that has mean latency of 250 milliseconds and has 50 milliseconds of standard deviation. When the mean value of the network latency is increased to 1 second, we can see that all protocols need more time to reach a consensus, and most of them are using more messages to reach a consensus. When the standard deviation is increased to 300 milliseconds, the performance of most BFT protocols also worsened. We can also see that Hsiao, as a state-of-the-art BFT protocol, always uses the least amount of time and messages, which aligns with the theoretical analysis result. However, when the standard deviation is increased to 1 second, the time usage of Hsiao is significantly increased. This shows that Hsiao's naive synchronizer cannot handle an unstable network efficiently, causing other protocols, such as PBFT and Libra BFT, to outperform Hsiao. This experiment is checking BFT protocols' performance when some of the participating nodes are fail-stop nodes. The x-axis is the type of the BFT protocol, and the y-axis is the time usage of these protocols. We gradually increase the number of fail stop nodes, and we can see that when there are less than 3 fail stop nodes, Hsiao has the best performance among these protocols. However, Hsiao's naive synchronizer has a huge efficiency degradation when the number of fail stop nodes increases to more than 3 nodes. This is because the naive synchronizer cannot easily keep the honest nodes in the same leader, and when the number of honest nodes is decreased, it needs much longer time for them to synchronize to the same leader. This experiment is comparing the execution time of BFT protocols when they are under a network partition attack. The network partition is resolved 60 seconds after the execution, and most BFT protocols can reach a consensus almost immediately after the partition is resolved. However, Hsiao with a naive synchronizer spend much longer time to reach a consensus even when the partition is resolved. This is because this synchronizer uses a view doubling mechanism that exponentially grows its timeout when no consensus is reached, and so the timeout grows to a large value during the attack. After the partition is resolved, it still needs to wait for another long timeout before it can finally reach a consensus. Apart from calculating the time and message usage of BFT protocols, our simulator can also automatically generate a diagram of the execution trace of each node. This diagram is drawn by our visualization tool when we simulate Hsiao using 4 honest nodes and no attacker nodes. The y-axis indicates the ID of each node, and the x-axis is the time elapsed since the simulation starts. The black lines between nodes are the protocol messages they transmitted, and the color of each node indicates the current leader. The red stars indicate when enough vote is scattered by a leader, thus the round is successful, and the yellow diamonds represent the time when the consensus is reached. Using this diagram, we can visualize the view doubling mechanism used by Hsiao's naive view synchronizer. Initially, the timeout is set to around 500 milliseconds, and if no consensus is reached before the timeout occurs, honest nodes will double their timeout and switch to the next leader. Therefore, we can see that these nodes double their timeout and change from leader 1 to leader 2 after around 500 milliseconds when the first timeout occurs, and now the timeout is around 1 second. However, they still cannot reach a consensus before the next timeout occurs. These nodes then switch to the leader 3, and the timeout is doubled once again to around 2 seconds, and these nodes can finally reach a consensus after around 1.5 seconds. Using this diagram, we can clearly see that timeout grows exponentially when no consensus is reached. This functionality can also help researchers study the behavior of other BFT protocols. In conclusion, there are 3 points that I want to stress here. First, simulation has several advantages over other methods, such as more efficient, support various environments, and easier to deploy. Second, our simulator supports a wide range of BFT protocols and attacks, and it has much better performance than existing work. Third, our simulator allows us to discover interesting behavior of BFT protocols, and we anticipate it to empower future research. Thank you for watching our video. Please refer to our paper and our GitHub repo for more information.